Okay, we are on to chapter 8. So this is exam 3 stuff. So start a new sort of exam chapter. We're going to talk about chemical composition. We're going to talk about some important calculations that we use a lot here in chemistry. So let's get into it. Now, the first thing we're going to talk about is atomic mass, and atomic mass is one of those fundamental properties of an atom. It's related to obviously the protons, electrons, and neutrons, but atoms are extremely small particles, so we really can't sort of weigh them or anything like that. You can't just take a single atom and put them on a scale. So what happens usually when you have a situation like that where you can't sort of directly measure something, a lot of times they will choose something to be used as a standard to sort of compare everything to. And for atomic mass, they use a isotope of carbon, which is the carbon 12 isotope. And the carbon 12 isotope has exactly a mass of 12.00 AMU. And AMU is a unit of mass, which is known as an atomic mass unit. It's also sometimes called a Dalton. And that is sort of what they compared everybody else to and used as a standard to figure out all the atomic masses. By the way, the atomic masses are what we find on the periodic table on the bottom here, and that is the atomic mass. Remember, again, it is not the mass number, but that is where we do find that sort of number located. So what they did was they showed through experiments that something like hydrogen is only about 8.4% as massive as the carbon 12 standard isotope. So they just did a little bit of math here. They took about 8.4%, converted it into a decimal, times it by 12, and they came up with 1.008, which again is what we see on the periodic table for the atomic mass of hydrogen. Similar calculations were done for other elements that are up there. 16 for AMU for oxygen, 55.85 AMU for iron. Now, as we will see, we oftentimes will not kind of use that number with AMU. It's not really a convenient unit for what we do, and we will see that number a little later on in this chapter. We will use it with grams and grams per mole, which grams are a more sort of useful number. So once again, if you go to the periodic table, you can find that. And sort of the conversion that you could get from that is there is 1.008 AMU per atom of hydrogen. So that's sort of the relationship that you could have in that case. And one way that you can kind of pull that off the periodic table. Typically speaking, when we do pull that number off the periodic table, it is 4 significant figures is what we use. Now, you may be wondering if the carbon 12 isotope is the standard that was used for atomic masses, and it has a mass of 12.00. Why do, when you look at carbon on the periodic table, it doesn't say 12.00, it says 12.01? And really, what we do see on the periodic table is what is known as the average atomic masses. And what they're the average of are all the naturally occurring isotopes for those particular elements. So a reminder that isotopes, right, are the same element, but they have different numbers of neutrons, and they have different masses because they have different numbers of neutrons, as the neutron is the heaviest of proton, electron, and neutrons in the atom. So what they are seeing is those averagely occurring, naturally occurring isotopes and the average mass of it. And how we sort of calculate that and how that calculation is done is if you want to kind of calculate the atomic mass in AMU, you basically take the percent abundance of the first isotope and you times it by the atomic mass of the first isotope. You then add it to the percent abundance of the second isotope, and you times it by the atomic mass of the second isotope. And you basically just keep following that pattern. If there's 3 naturally occurring isotopes, you would then do it for the third one and so forth. The key on this one, though, is I'll go atomic mass here of the second isotope. And then, like I said, you just kind of repeat it. The key is you're actually adding in between that calculation. You're not multiplying. And the percent abundance or the relative abundance of those isotopes is basically the percentage at which they occur naturally. So when we look at something like carbon, there's actually the carbon-12 isotope, which occurs about 98%, 99% of the time. And there's about the carbon-13 isotope that occurs about 1% of the time. And those are the naturally occurring isotopes. And those are what makes up the actual value that we see on the periodic table. So as you can see here, we can see that the natural abundance of carbon-12 is about 99%, 98.89%, and 1.11% for carbon-13. You can also see that the mass here of the carbon-13 isotope is not 12, it is 13.00335. So we could do our calculation. So this is 98% converted into a decimal. You could obviously divide it by 100 or just move the decimal place 2 places to the left. Times it by the first isotope's mass, which is carbon-12. This is our 1.1% converted into a decimal, times by the atomic mass there of our second isotope in this particular case. And if you do that, you do get the 12.01 that we do see on the periodic table. So what we are seeing up there are the average atomic masses, again, of all those naturally occurring isotopes for that particular element. By the way, when you add up the percent abundance or relative abundance, it should probably add up to about 100%, right? That way you have all the naturally occurring isotopes in that particular case. Question on that there. Now, it's important to remember, as I mentioned, that these are average values, which means in reality, oh, yeah. Yeah. On the previous slide or this, yeah. On the next slide back. Yeah, yeah. Yeah. Whoops, there you go. So again, basically, you're just going to take the percentage of each isotope times by the atomic mass of each isotope, and then add it to the percentage of the next isotope times, obviously, the atomic mass of the next isotope. The key there is you do have to convert the percentage into a decimal. So again, you could either divide by 100 or move the decimal place 2 places to the left. Yep. So as I was saying, you should remember that you will actually never really find a carbon isotope with a mass of 12.01. If you were to get a bunch of carbons together, you would take them out. They would either be a carbon-12 isotope that has a mass of 12, or they'd be like the carbon-13 isotope that has a mass of 13. You'll never really find one that has a mass of 12.01. Again, just sort of an average value of all those naturally occurring isotopes for carbon. So why don't we try one here? Why don't you try the calculation on this? Bromine 79 is 50.70% and has a mass of 79.92 AMU, while bromine 81 is 49.32% and has a mass of 80.92 AMU. What would be the atomic mass of bromine? So use that formula we just. Okay, let's take a look. So again, we basically have 2 isotopes here. We got bromine 79 and bromine 81. Remember the 79 and 81 are the mass numbers here. We do have the percentages at which they occur. So once again, just kind of quickly, you should always kind of just look at the percentages, like I said, and it really should add up pretty close to 100. It may not be perfect at 100, maybe 99-ish, 98, a little bit over 100, but definitely should be in the 100 range. Otherwise, you are definitely probably missing an isotope somewhere along the way there to do the calculation. So what we're going to do to calculate the atomic mass is we're just going to take each isotope And we're going to take the percentage here, and you could either divide it by 100% or just simply move the decimal 2 places to the left, and you're going to times that percentage, which is 50.70 times the atomic mass of our first isotope. You then are going to add it to the percentage of the second isotope. And once again, if you don't want to move the decimal, you can also just, like I said, divide it by 100 and it will move the decimal for you. And you times it by 80.92 AMU in this case. And if you do that, you're going to end up with here. We'll end up here for this particular one of 80.43 AMU in this particular case. Any questions on that calculation? Okay. All right, so why don't you try one more here? An isotope that has 70.5% abundant with an atomic mass of 117.80, while the other isotope has an abundance of 29.5% and an atomic mass of 120.85 AMU. What is the atomic mass here? Okay, let's take a look again. We have two isotopes here. We got one that's 70.5% and one is about 30%. So that's almost 100%. That should be. So again, to calculate it here, we're just going to go each isotope here. So our first one, I'm going to move the decimal place 2 places to the left and times it by the atomic mass of our first isotope. So that's our first isotope. We're going to add it to, again, moving the decimal point 2 places to the left to convert our percentage into a decimal. Going to times it by the molar mass here of our second isotope. And then we should end up with something here. Let's see. And we'll end up with about 118.9 AMU in this case. Yeah. Any questions on that there? So this is calculation, how they get really the numbers that you see on the periodic table. Let's talk a little bit more about some of these numbers here. Atoms are very tiny in mass, so to avoid using very small numbers, we do use sometimes the atomic mass unit, which is AMU. The relationship between atomic mass unit and grams, as you can see there, is 1 AMU is 1.66 times 10 to the minus 24 grams. So again, although we don't really use atomic mass units all that much in calculations, we will use more of a grams unit along the way. As I mentioned, you can take from the periodic table the atomic mass and use as a conversion factor. So again, when you do see that bottom number, as we talked about a second ago, that is again basically how many AMUs there are per atom is basically the conversion factor. So if we want to know the mass of 431 atoms of carbon, we would just do our dimensional analysis here. We would have atoms up on top. We would use our conversion factor here like so that the atoms cancel each other just like normal. We would multiply and then divide, and that would give us something like 5176 AMU is the atomic mass of that many atoms of carbon. Same thing here for aluminum. If we go to aluminum, what we will see on the periodic table is 2698 written there. That again is what we could pull off and use as a conversion factor, 2698 AMU per atom. We also could flip it around again, like any conversion factor if we needed to, and put the atoms on top and the 2698 AMU on the bottom. So if we're looking for 75 atoms, what is the mass again? Using dimensional analysis, this is on top, so atoms will cancel. We're going to multiply here. Obviously, nothing much to divide by on the bottom. And that will get us 2024 in terms of the atomic mass of that many atoms. So again, that is a conversion factor you could use. I'll be honest with you, you probably will not use that conversion factor all that much in that form. as I mentioned before, we usually use it in a different form, which is known as molar mass, where we can use something like grams, which again is a more useful sort of unit for us. So let's see here, flip the page. Maybe there you go. So let's talk about kind of the more useful sort of conversions that we definitely will use, which is molar mass and Avogadro's number. And molar mass and Avogadro's number can be thought of as conversions. They are essentially conversion factors that are used to convert to different things. So the first thing we're going to talk about is the idea of the mole. The mole, not the furry guy, the mole is a word that is used in chemistry to basically represent a certain amount of something. So in life, we have words that do represent like a number. If you say you have a pair of something, that usually means you got two of something. If you say you have a dozen of donuts there, you got 12 donuts. If you have a gross of pencils, is what they used to use that a lot of. That means you have 144 pencils. So in chemistry, the word that we use to represent a certain amount of something is the mole. And by the way, the abbreviation for the mole is MOL. So when you do see MOL, that is actually the abbreviation for mole. It is not molecules. And it's a very common mistake that people, when they see MOL, they oftentimes think molecules. In chemistry, for the most part, if they're talking about molecules, they will write out the word molecules. And if they're talking about moles, they'll just write MOL. Most of the time, they drop the E off of it there, and that is sort of the abbreviation. So a mole represents really the amount of elementary substances there are basically in 12 grams of the carbon 12 isotope. That standard that was used for the atomic mass. And really, what a mole equals is our friend Avogadro's number. And 1 mole of anything will equal Avogadro's number, which is 6.022 times 10 to the 23. Now, the units associated with Avogadro's number does change. These could be atoms. These could be molecules. These could be particles. These could be pizzas. These could be shoes, whatever it may be. I would say most of the time, these are the two units you're going to see. You're going to see atoms and you're going to see molecules as the units. And this is really a conversion factor. And you can write this as a conversion factor. You can say 1 mole of something has 6.022 times 10 to the 23 atoms. Or you could flip it around, 6.022 times 10 to the 23 atoms has 1 mole. And this is our conversion factor to go from moles to atoms are molecules, usually, and backwards. So if you need to do that sort of conversion, you need to go from moles to atoms or moles to molecules, or if you're starting with atoms or molecules and you need to go back to moles, Avogadro's number is your conversion factor to do that. And we do use this number here to 6.022 times 10 to the 23. Obviously, like everything else here, you do need to know that number, 6.022 times 10 to the 23. You should not use Avogadro's number in every calculation, and that's also a very common mistake that people make. They learn this number and they just want to kind of use it in every calculation that they are doing. And you should not do that. You should only use Avogadro's number if somewhere in the problem they give you a number that's in atoms, they give you a number that's in molecules, or they ask you to calculate something that's in atoms or molecules. If you really don't see those kind of keywords in the calculation or the problem, you really should just leave Avogadro's number on the side and not use it. Again, that's one of the problems. It's kind of overused in the wrong situations and stuff like that along the way. Any questions on that there? Now, like I said, Avogadro's number does mean how much you have. So you could take anybody off the periodic table and you could say in 1 mole of hydrogen, there would be 6.022 times 10 to the 23 atoms of hydrogen. You could do it for carbon too. and 1 mole of carbon, there will be 6.022 times 10 to the 23 atoms of carbon. Again, these could be used as conversion factors. By the way, if you had a compound like water or a molecule like water, you could say in 1 mole of water, there are 6.022 times 10 to the 23. The difference here is, as I was talking about a second ago, we would not use atoms here because water is not an atom, water is a molecule. So the units of Avogadro's number would actually be molecules in this case, because again, water is a molecule. If you had CH4, same deal. 1 mole of CH4 will equal 6.022 times 10 to the 23 molecules in this case. So we use it for molecules, we use it for atoms, and again, like I said, the kind of units associated with the 6.022 can definitely change. And again, you can use any of these as conversion factors, basically, to do those conversions. You can write 2 fractions and use them as a conversion factor. Again, it would look something like 1 mole of water over 6.022 times 10 to the 23 molecules. Or you could put Avogadro's number up on top as a conversion factor, 6.022 times 10 to the 23 molecules in a mole of water. So again, use any of those as conversion factors. To do that conversion, we were just talking about going from moles to molecules, moles to atoms are backwards. Any questions on that there? All right, let's talk about really the probably most common calculation that you're going to use, or really conversion factors that you're going to use, and that is molar mass. And molar mass is the units of molar mass are these units. They are grams per mole. And the molar mass is really how many grams there are of a substance per mole. And basically, where we get the molar mass is from the periodic table. And numerically speaking, with conversions, the atomic mass that we see on the bottom here, which was, as we just saw, 1.008 AMU per atom, is numerically equal to the molar mass, which for hydrogen would be 1.008 grams per mole. So that is the unit that we really do use off the periodic table the most. We use the bottom number in most cases as the molar mass. Again, the reason for that is grams is a more convenient unit that we use, right? When you go measure something on the balance, it doesn't give you the mass in AMU, it gives you the mass in grams. So this sort of molar mass is a very useful unit. It is found from the periodic table. And again, it is numerically equal to the atomic mass in AMU per atom as you get there. Once again, same rule applies. We typically only take 4 significant figures off the periodic table when we use that. Molar mass is our conversion to go from grams to moles, or backwards, moles to grams. So that is our conversion factor to do so. And same deal, you could take any element off the periodic table there, like carbon, and that would be the molar mass of carbon is 12.01 grams per mole. You could also use this obviously as a conversion factor. If you needed to flip it around, you could put the moles on top and the 12.01 grams on the bottom. So we do use it as a conversion factor. Now, if you had something, say, like water, and you needed the molar mass of water, what you would do is essentially just add up all the parts from the periodic table. So you would go to the periodic table and you would find hydrogen. And again, it says 1.008 grams per mole is the molar mass of hydrogen. There are 2 hydrogens here, so we have to multiply that by 2. We would then add it to our 1 oxygen that is present. And if you go to the periodic table there for oxygen, you will see 16 written down there. And that would give us 16.00 grams per mole. Adding that together gives us the molar mass of water of 18.02 grams per mole. So this is the molar mass of water. You just basically add up all the parts if it's a molecule. Also can be used as a conversion factor. So if you needed to, you could flip this around, put the moles on top, 18.02 grams on the bottom. And again, you could use it either way. If you were asked what is the molar mass of water, this would be the correct answer in this version, 18.02 grams per mole. The number always stays with the grams part, and the moles is always per 1 mole. So that is always the way molar mass is written, number with the grams, and it's always per 1 mole. So if you had something like C2H5O and we wanted the molar mass, all we're going to do again is just add up all the parts. We would go to the periodic table, find carbon, and we would go 2 times the molar mass of carbon, which is 12.01 for our carbon. We would then add it to, there are 5 hydrogens, 5 times the molar mass of hydrogen from the periodic table, the 1.008 grams per mole. And we would add it to our 1 oxygen, which is 16 grams per mole. This is going to give us a molar mass here of 2 times 12.01 plus 1.008 times 5 and a 16. So 45.06 grams per mole would be the molar mass of this particular compound. Again, you could just add up all the parts. Any questions on how to calculate the molar mass? Again, it's important to know how to calculate the molar mass, and then obviously you will most likely use it as a conversion factor, and you can take dimensional analysis, opposites cancel, to use it to convert into something. So if you had grams and you wanted moles, you would divide by the molar mass. So you take the grams per mole. This would be our molar mass. And the grams would cancel, and that would give you moles. If you had moles and you wanted grams, you would actually multiply by the molar mass. And the moles will cancel, and that's going to give you grams. So again, that is probably how you're going to use molar mass as a conversion factor, and again, the way to kind of set that up. How do these all relate to each other? Well, if you have 1 mole of hydrogen, that would contain 6.022 times 10 to the 23 atoms of hydrogen. And that would also have 1.008 grams of hydrogens. That's how they all relate to each other. Same thing if you had 1 mole of water, that would have 6.022 times 10 to the 23 molecules of water. And that many molecules of water would represent 18.02 grams of water. So they are related to each other. If you're going all the way from grams to like atoms, the process here would be grams to moles using the molar mass as a conversion factor, and then moles to atoms using Avogadro's number. Right? Obviously, same conversion if you're going the opposite direction. You go from atoms to moles, and then moles back to grams. You would use the same conversion factor. So the moles is what kind of ties both of those together. The grams and the atoms are the molecules. Again, this could be molecules as well instead of atoms. So again, as I mentioned, you definitely don't want to kind of overuse Avogadro's number or use it in the wrong situation. So again, if there's no mention of atoms or molecules, just leave it on the side. If it's just about grams and moles, it's molar mass is your conversion factor all day, and that is what you get from the periodic table. Any questions on that? I'm not sure what you mean about correctly. So what in terms of yeah. Yeah. So this, if you're asking about this, this is the calculation to calculate the actual molar mass of water, which you would have to do because you won't know the molar mass of everything, right? So you would have to do that calculation. So you do need to do that calculation to get that 18.02. Then once you have that 18.02, you most likely will use it in a calculation like up here in one of those versions. The 18.02 would be this number here on each of these calculations, and you would use it as a conversion factor in a problem is most likely. You would use it to either convert grams to moles or moles to grams is how you would use it. So for example, if you had, let's just say we had, hey, we had, let's do, let's say we have 12.3 moles of water, and we want to know how many grams of water does that represent, right? So what we would do if we didn't know the molar mass of water, we'd obviously roll through the periodic table and do our calculation like we did on that previous page, where we look up the mass of the two hydrogens, we get the mass there of our oxygen. That gives us our 18.02 grams per mole, which again is our molar mass of water and really our conversion factor. At this point, we would just do it like a conversion problem. We would start with the 12.3 moles of water. Again, opposites cancel, so basically moles are on top. So we do need to use the molar mass exactly the way it's written, like so. We're going to multiply just like normal when we do dimensional analysis, right? Moles are going to cancel, and that would tell us in this case that 12.3 times 18.02, there are 221.6 grams of water in that. We would still look at sig figs, by the way, and that would be 3 sig figs, and it actually would be something like 222 grams of water on sort of the round of that. Now, that would be really how you would use the molar mass, as you see there, as really just a conversion factor and sort of like a dimensional analysis sort of situation is most likely how you would use it. And if we want to know how many molecules that was, for example, we could take this calculation one more step of the way. And because we are looking for molecules at this point, that puts Avogadro's number into play. And we know that for 1 mole of anything like water, there is 6.022 times 10 to the 23 molecules. And we could just continue on with our calculation. We could use the 222 grams of water. And actually, no, we wouldn't in that case. We wanted moles. We would actually use our original number there. We would use our 12.3 moles of water, which is we already know what that is. We would use our Avogadro's number as a conversion factor, 1 mole of water, 6.022 times 10 to the 23 molecules of water. Again, using it like a dimensional analysis, multiplying the top, dividing the bottom, the moles are going to cancel, and we will end up with 12.3 times 6.022 to the 23. So this many moles of water represents 7.41 times 10 to the 24 molecules of water. So as you can see, we have over 18.02 grams of water in this case, and we definitely have a lot more than that, and that means we have a lot more molecules of water in this case. We have 7.41 times 10 to 24 molecules of water. So again, both of these things are essentially going to be conversion factors that are used to kind of go between these units, and either most of the time molar mass is probably going to be the one that you're going to use the most. Any questions on that there? We use this is the molar mass, which is numerically equal to the atomic mass, and we use that as a conversion factor to convert. If you know how many moles you have of some of water, for example, or you know how many grams you have of water, the molar mass is what you would use to go between grams and moles. So it's the conversion factor that is used to go between those two units for anything. If you have grams, you want moles, or you have moles, you want grams. The molar mass from the periodic table is what you use to kind of use as a conversion factor to go between them. The only time you would use Avogadro's number is if you've got to go from moles to atoms or moles to molecules or backwards. That's when you would use Avogadro's number as a conversion factor to do that. Correct. Yeah. So basically, what this means when you look at the molar mass, it means if you have 1 mole of water, there's 18 grams basically in there. In this case, we had about 12 moles of water, right? So in that 12 moles of water, there's not 18 grams, there would be 222 grams. And we're using the molar mass conversion factor to figure that out. Same thing down here. In 1 mole of water, there's 6.022 times 10 to 23 molecules floating around. In this case, we don't have 1 mole, we got about 12 moles of it. And you can see there's a lot more molecules of water floating around in that case. And again, we're using the Avogadro number as a conversion factor to figure out how many molecules there would be in that particular case. Yep.